guys, Timmy coming at you here, and today what I want to do is I want to explain to you how a neuron, generates an electrical impulse and is able to transmit that to other nerves or other cells of the body. Now, if you look at a nerve, you have the axon. The axon is what transmits that electrical signal down to the end of that little knob there, where it releases a specific neurotransmitter. In the case of a motor nerve, the neurotransmitter that's released there is acetylcholine. So what I'm going to try and explain to you today is how this nerve actually generates an electrical impulse. Now, look, one of the things that you have to understand is, and you learned this in AMP, now probably you did, that on motor nerves there are these little bare spots called nodes of Ranvier, and the other parts, not the bare spots, are covered by this myelin sheath. In this little picture, it looks like a blue hot dog wrapped in a bun and then a big glob of mustard. Anyways, I digress. My point is that the electrical impulses that are generated in the axon are actually produced in the nodes of Ranvier. And when this little node produces an electrical impulse, an action potential, it's going to cause the next node to produce an action potential, an electrical impulse. And they tell two friends, and so on, all the way down to the end of the line. Now, what I'm going to do is I'm going to take this little piece right here, and I'm going to blow it up for you in a slide. Now, I'm not the greatest drawer, that much is true, but hopefully it'll help. So let's take a closer look at the node of Ranvier. So here's the myelin sheath you're looking at right here. And then this is the bare spot, the node of Ranvier. And ladies and gentlemen, unfortunately, the devil is in the details. And if you truly want to understand fluid and electrolyte disturbances, you have to understand how electrolytes move into and out of a cell. There's no other way of getting around it. If you want to sit and try to memorize all the different signs and symptoms associated with these electrolyte disturbances, well, have at it. My point is that if you understand this, and again, it's not life-changing. It's not rocket science. If you understand this, then you can understand what happens if there are electrolyte disturbances, high or low electrolytes, how it will affect the nerves, how it will affect the heart, how it will affect the brain, and the body in general. So let's go at it. First of all, if this is the membrane, the cell membrane of the node of Ranvier, embedded in the cell membrane of the node of Ranvier are these little protein channels. Now, sodium and potassium can't simply leak in and out of the cell. They have to have a way to get in. So embedded in the node of Ranvier are these little protein channels called, you're not going to believe this, sodium ion leak channels. And because sodium is highly concentrated in the blood, it wants to go from high concentration in the blood to low concentration in the cell. And the only way that it can do that is by going through a sodium ion channel. Now, potassium is highly concentrated in the cell. Where does potassium go? Potassium wants to leave and go into the blood. Well, again, potassium can't just willy-nilly go through the membrane of this node and end up in the blood. Instead, it has to go through a specific protein ion leak channel that's embedded in the cell membrane. And again, the this is really important. These guys are specific. The only thing that can go through a potassium ion leak channel is, yep, you got it, potassium. And the only thing that can go through a sodium ion leak channel is sodium. Now, the other thing that you have to remember is that potassium is like 100 times more permeable than sodium. That means that for every 100 potassiums that leave, only 1 sodium enters. So how I like to do it in my class, and the students kind of balk at this, but I think it's a great idea. So what I tell them to do is that every day, so the student would be the inside of the node of RANVA. Every day when they come into class, they have to give me $100. So Timmy is the blood and you is inside the cell, the node of RANVA. So every day you come in, you give me $100. I think it's a great idea. And when you leave, I give each one of you $1 back. So at the end of the semester, who is going to be positive and who's going to be negative? Well, I got up early this morning to make sure that I did this right, so it always works out that Timmy is ahead. So the fact that potassium is much more permeable than sodium allows you to have a difference in electrical charge across a cell membrane. And because you have a difference in electrical charge across the cell membrane, that cell has the potential to produce electricity. Now, the other thing that's embedded in all your cells are this little guy here called the sodium-potassium pump. Now, again, think about this for a minute. Sodium wants to naturally leak in through a sodium ion channel so that there's equal amounts of sodium in the blood and in the cell. The fact is that there's a lot more sodium in the blood than in the cell. That's because of our buddy, our pal, the sodium-potassium pump. So when sodium leaks in, that pump takes 3 sodiums and pumps them back out. So you're going against the current. So if you've ever made a whirlpool in a round pool, you know, your friends when you're little get around and you start going and swimming in the same direction, and then you get this nice little whirlpool started. Well, once you pick your legs up and you kind of ball yourself up, that current's going to take you, so you don't have to exert any energy. But in this case, you are moving against the current. So you turn around the pool and you try to walk against the current. To keep your spot where you were, you got to work against the current and expend some energy. So because you're pumping against the concentration gradient, right? You're working against the current. That requires ATP. So ATP is used by the sodium-potassium pump. And to a large degree, the sodium-potassium pump contributes a lot to your overall metabolism in your body. So about 20-25% of everything you put into your pie hole goes to making ATP to make the sodium-potassium pump run in all your cells. So this guy is important. Now here's the other thing. When sodium leaks in, it's going to take all those sodiums that leaked in, it's going to take 3 of them and pump them back out. And the potassium that leaked out, it's going to take 2 of those potassiums and pump them back in. And again, you're working against the concentration gradient because potassium is highly concentrated in the cell. And that sodium-potassium pump needs ATP in order to work. And the question that should immediately come up is, well, why 3 sodiums and 2 potassiums? That's to allow for that positive on the outside and negative on the inside. So we'll do this again. every time you come into class, in addition to the $100, you're going to give me $3, and then when you leave, I'll give you $2 back. So this is what sets up what's referred to as the resting membrane potential. So the resting membrane potential is achieved by potassium leaking out, sodium leaking in, but the fact that potassium is much more permeable than sodium. So more positive things are leaving than entering. So the charge on the outside of the membrane is going to be positive, and because there's less positively charged particles on the inside compared to the outside, the inside is going to be negative. And to help reestablish and help maintain that resting membrane potential, you have our buddy, our pal, the sodium potassium pump. And that is because it goes against the concentration gradient, that requires energy. So you see these other things in here that look like, I don't know what they look like, but anyways, these guys right here are what are referred to as voltage gated channels. Now, as the name implies, voltage gated channels, so you got a sodium voltage gated channel and a potassium voltage gated channel. As the name implies, these little channels will open or close when a critical voltage is reached inside that cell. And each one, the sodium voltage gated channel, opens and closes at a different critical voltage inside that cell, inside that node. And a potassium voltage gated channel, it is going to open or close at a different critical voltage inside that cell. And each one of these voltage gated channels open and close at a different voltage. So that's what allows the electrolytes to flood in or out. Now, think about this. These ion leak channels leak, right? If you got a leak in your basement, a little water comes in, okay, no big deal. But if the wall starts tumbling down, right, water will flood in. So when you open up voltage gated channels, that's what causes the ions to either flood in or out depending on which voltage gated channel is open. So if a sodium voltage gated channel opens, and you can open it, or at least I can, simply by taking this eraser and erasing it, see? When you open that up, right, that means tons of sodium, tons of it, going to rush into that node, and that's going to make the charge inside that cell much more positive. And when a voltage gated potassium channel opens, the same thing happens. Potassium, tons of potassium rush out. So the voltage gated channels are involved in repolarization and depolarization of that node. That's what produces the electrical impulse. That's what produces the action potential. And you know, a lot of these terms, I think that's the problem. Students kind of get bogged down with these terms. So I will use the term and then try to give you a simpler definition. So let's talk about this now. All right, so watch. The resting membrane potential. If you are resting, you are doing nothing. So many of my students, they have a resting membrane potential in my class. That means they're doing nothing. I'm just playing. So watch. A resting membrane potential is the charge inside this node when it's doing nothing. How is that achieved? It's achieved by sodium leaking in through these leak channels, potassium leaking out, and then our buddy, our pal, the sodium potassium pump. And remember that potassium is much more permeable, about 100 times more permeable. So that's going to make the inside negative compared to the outside. So what you got is a negative charge inside that node compared to the outside. And that's the resting membrane potential. it's always negative. I don't care about a number, it's just always negative. Now, in order for this little node to fire, you have to develop a critical voltage inside that node. So if you're a nerve and you want to fire, you have to apply a stimulus to that nerve. So if you touch yourself appropriately, right, that's when you stimulate, right, you touch your skin. That causes sodium to begin to leak in to that node through those sodium leak channels. And because sodium's positive, it's going to cause the charge inside that cell to become more positive. So you're moving on this little graph, and you've seen these in your book, right? You got the resting membrane potential, it's negative. But if you add a positive charge, the charge inside that cell is going to become more positive. Now, if the stimulus is strong enough, right? You touched your arm strong enough where enough sodium leaks in and is able to bring that charge inside that node to threshold. Boom. At threshold, this is what activates the voltage gated sodium channels. So at threshold, what happens? At threshold, right, sodium leaked in because you have stimulated that nerve. That's going to activate sodium voltage gated channels. It's going to open up sodium voltage gated channels. So they're going to open up. And what does that sodium do? It doesn't leak in, it floods in. Bam! So tons of sodium going to rush inside that node. And because sodium has a positive charge, what's it going to do? It's going to cause the charge inside that node to become much more positive rapidly. So there's an increase in the charge inside that cell because you opened up the sodium voltage gated channel. And that, ladies and gentlemen, is called depolarization. The nerve has fired. So sodium causes depolarization, and specifically it's the opening of the sodium voltage gated channels. Now, as sodium begins to rush in, you're going to hit inside that node another critical voltage. And when that critical voltage is reached, when that critical voltage is reached, this is what happens. That's going to cause the voltage gated sodium channel to close. And then it's going to open the voltage gated potassium channel. And when that voltage gated potassium channel opens, again, voltage gate, flood out, tons of potassium is going to flood from the node into the blood. And because potassium's positive and you're taking it away from the inside of the node, the charge inside that node is going to become more negative. So that's going to, when the voltage gated potassium channels open and the voltage gated sodium channels close, the charge inside that cell is going to become more negative, and it's going to come back towards the resting membrane potential. So the opening of the voltage gated potassium channel causes that node to repolarize or reset itself. Now, the voltage-gated potassium channels remain open long enough for that charge inside that cell to actually be lower. It's actually now more negative than resting, and I'll explain that, why that's important in a minute. This is called hyperpolarization or overshoot, and then it's the job of the sodium-potassium pump and the leak channels to get it back to resting so that it can fire again. So what's really important is to know that sodium is involved in the depolarization of nerves and potassium is involved in the repolarization of that nerve. So let me explain why that hyperpolarization is good. Watch. Remember I told you that, alright, this node right here, right? That's a bad color. This node right here is going to fire. And when it fires, it causes the next node to become leaky to sodium. And when that node becomes leaky to sodium, if enough sodium leaks in, it's going to cause that node to fire. And then it's going to cause this node to become leaky to sodium, and it's going to fire. Now watch. When this node fires, if this node that already fired was back to resting, it wasn't hyperpolarized, when this node fired, it would cause this node to fire and then this node to fire. So you'd have this back and forth spread of that electrical impulse. So by becoming hyperpolarized, right, more negative after it fires, it prevents that from firing again. And that's a good thing because that guarantees that that electrical impulse is only going to go in one direction. Fine example of the body doing stuff that makes sense. So what I'm going to do is I'm going to leave it at that right now. So again, understanding how electrolytes move into and out of cells, in this case the little node of a RANVA of a nerve, that's going to help you understand some electrolyte disturbances. What I'm going to cover next is the hyper and hypokalemia, so how those affect nerves. Alright, I hope this helps.